Okay, I guess it's time to go again. I guess everybody knows everything there is to know about block codes now. So we're going to start this afternoon and tomorrow morning on convolutional codes. So these are just some of the topics we'll discuss this afternoon. So a convolutional coder, as we indicated briefly yesterday, processes an information sequence continuously rather than kind of block by block like is done in a block code. So we have an n-bit encoder, that puts out n bits at a time. And in a block code, it depends. Those outputs depend only on the k input bits at that time. But in a convolutional code, the outputs depend on the k input bits at that time plus the k input bits in some number of previous blocks. M is what we use, and it's called the memory order of the encoder. So a convolutional encoder simply has memory, and a block coder doesn't. A block encoder, if you like, is implemented as a combinational logic circuit, and a convolutional encoder is implemented with sequential logic. So that's the basic difference. So the set of output sequences produced by the encoder is called the code. So the code words are sequences, so they don't have a fixed block length like they do in a block code. They can be of any length. We'll see this as we go through. And the particular values of n and k are typically small for convolutional codes. For block codes, particularly if you want a powerful code, you're going to need big values of n and k. But for a convolutional code, you can get a powerful code by using small values of n and k and large values of m. So the strength of a convolutional code really comes from the memory, or a related parameter called the constraint length, compared to the actual values of n and k, which is the number of bits in and out at each time unit. So that's different from block codes in that regard. So we had looked at this example yesterday. This is just a cake 1 n equal 2 with memory 2, which means the encoder has two delay elements here. And this particular code formed its outputs by taking two different linear combinations, the current input and two past inputs. So the first output bit is the sum of the current input bit and the input bit 2 time units in the past, and that's stored here, okay, because it's been delayed twice. And we see that sum represented up here. And the second output bit is the sum of the current input bit, which comes in here, the previous input bit, 1 time unit in the past, which is now stored here, and the time unit and the input bit 2 time units in the past, which is stored here, and we see that sum represented here. Again, all these are modulo 2 addition, all these operations. So it's kind of straightforward, at least for simple encoders, to draw the encoder diagram based on the equations. Or if you've given the encoder diagram, you can write down the equation. Now, nu sub I, we generally call the length of the ith shift register. Now, if an encoder has more than one input sequence, a little example we had there just had one input sequence, but k can be bigger than 1. I said k is not going to be large, it's going to be small, but there are codes in practice that are used with values of k 2, 3, maybe even 4 or 5 at some point. So each of the input sequences in a convolutional encoder is assigned a separate shift register, at least in kind of the standard way that encoders are realized. We'll talk more about that later. And each of these shift registers has a certain length, nu sub I. And the memory order of the encoder is the maximum value of nu sub I. Okay, so some of the shift registers, some of the input sequences may be delayed more than others, in other words. They don't all have to have the same amount of the length shift register associated with them. So M, again, is, as we said, the memory order of the code. The ratio k over n is the code rate. That's just because at every time unit we have k bits coming in and n bits coming out, so the ratio of information bits to code bits is k over n. That's the same as for block codes. Now the overall constraint length nu of an encoder is defined as the sum of these nu sub i's. So it's the total number of shift register stages in the encoder. Each input is associated with a shift register with nu sub I stages, and if we sum those up, we get the total number of shift register stages, total amount of memory, if you like. So there's a little distinction here. The memory order, M, is not the total memory in the encoder. It's the maximum memory associated with any input sequence. The total memory of the encoder is what we call this constraint length. Okay, and that's important because it relates to the complexity of encoding and decoding. Depends on the constraint length. So when we're encoding an N1 code, so k equal 1 here, we're just going to talk about k equal 1 for a while, one input sequence, just like this example that we've been showing. So we have one input sequence U, and notice that it doesn't have a fixed length. It's just a sequence of bits which could be of any length. So these codes are often, they find application in streaming problems where you're streaming data and you're not necessarily having things in blocks of a certain length, but just long streams of data. So they're kind of naturally useful for that type of application. So we have, in this case, a single information sequence, and probably most of the convolutional codes used in practice are of this type with k equal 1. All the wireless standards use k equal 1 convolutional codes. And again, the k equal 1 block code is almost trivial. There's only 2 code words. But in the convolutional code case, the strength of the code comes from the memory. And you can have very powerful codes if you have large memories associated with a k equal 1 code. So there are n output sequences here. We just use this notation to denote them. And again, there's sequences of indefinite length. And we can, if we want to, this is not necessary to think of it this way, but if we want to think of everything being combined into a single code sequence or a single code word, we can kind of interleave the output sequences together. So at each time unit, we'd take the n output bits coming at that time unit and indicate, say, at time unit 0, that would represent V0, and then the next n bits would be represented by V1, etc. So we can write the entire output sequence with one vector V like this if we like. You know, we don't have to do that. We could simply write the n output sequences separately like this if we want to also. There's several of these things in here that's just depending on what's a convenient way to write the sequences in a convolutional code. Now what kind of gives us our code or defines our code? Well, there is a set of n generator sequences, each of length m plus 1. M's the memory order. And they're denoted this way. And these are binary sequences again. This is very analogous to the generator matrix of a block code. And the output sequence, these are called convolutional codes for a reason, is the discrete time convolution of the input sequence with each of the generator sequences. So the ith output sequence would be this discrete time convolution where I is between 1 and n because we have n output sequences. So a discrete time convolution is just given by, we have the current output bit at the ith output is given by the current input bit times generator bit 0, and then the time unit, one time unit past input bit times generator bit 1 all the way to the input bit at m time units in the past times generator sequence bit m. Okay, and these generator bits here are the ones associated with the ith generator sequence, which generate the ith output. So this is just a compact way of representing this expression. Again, this is just modulo 2 addition, and the multiplication is just 1 times 1 is 1, and everything else is 0. So again, getting back to our example, this is a rate 1/2 convolutional code with memory 2. And in this case, the two generator sequences are 101 and 111. So that means that the first output is generated by this generator sequence, which means we take the current bit and we add to it the bit stored 2 time units in the past. That would be this bit, stored in the second stage of the shift register. And the second generator sequence is G2. And here we take, because these are all ones, we take the current input bit plus the one stored 1 time unit in the past plus the one stored 2 time units in the past, and that gives us our second output sequence. So again, you can go right from, previously we had kind of gone from, we kind of looked at the equations here, and those corresponded directly to the encoder diagram. Here we're kind of doing the same thing in a slightly different way, in that we look at the generator sequences, which of course do determine the equations, and we can write down the encoder diagram. So let's say we have an information sequence like this, and we would get the output, the two output sequences would be given by this. Now, we can, if we can remember what was on the previous slide, we have the first output sequence is always the sum of the current input bit plus the 1 2 time units in the past. So the first input bit is a 1. There's nothing in the past, so this bit's going to be a 1. The next input's going to be a 0. There's nothing 2 time units in the past, so this is going to be a 0. So we're kind of just, we're walking through discrete convolution now. The next input bit is a 1. 2 time units in the past is also a 1. 1 plus 1 is 0, so we get the 0. The next one is a 1. 2 time units in the past is a 0. 1 plus 0 is 1. So that's the way this sequence is generated. And notice we stop having 1s here. If it's a short input sequence, after this is just all 0s. Notice we can have a couple of more 1s come out of the encoder because of the memory. Otherwise, at this time unit, the current input bit's a 0. The 1 2 time units in the past is a 1, so we get this 1. And here we get 0 plus 1, which is 1. After that, there's no more 1s that are going to come out if these are all 0s. So the non-zero bits in the output sequences can go beyond the length of the non-zero bits in the input sequence by exactly m time units, 2 in this case, because of the memory in the encoder. And the same thing here. We just add the last 3 bits to get the current input bit in 2 past gives us 1 here. Current input bit in the 2 past gives us 1 here. Here we get the current input in the 2 past, so we got even parity here, so it gives us 0, etc. So that's just kind of walking through the discrete time convolution. And we can write, if we, again, we can just say this is the output, this is the code word, these 2 sequences. But if we want to put them together into one sequence, we could just take the 2 bits at time unit 0 and the 2 bits at time unit 1, just write it all as one sequence like that. Yes, okay. So there's a matrix way of representing a generator matrix that we can use for a convolutional code. Unlike a block code, it doesn't have a fixed size. It's got an undetermined number of rows and an undetermined number of columns, depending on the length of the input sequence that we're going to use. Okay, the number of rows is always going to be equal to the length of the input sequence. And the number of columns will be the length of the input sequence well, there's n columns for each input bit, and then you're going to go an extra m time units because of the memory, and that's the total number of columns you get. So the way the generator matrix looks is we had, now these are not the generator sequences. The notation is a little trickier, a little messier with convolutional codes, just because you've got to remember time, and you've got to remember, basically because you have to remember time, which you don't have to do in block codes. But these are the generator sequences themselves. These are, these are obtained from the generator sequences, and so G0 is the time 0 bits associated with each of the n generator sequences. Here's a typo. That should be a 2, I suppose. Yeah. For every time between 0 and m, we have a set of these generator coefficients that form these little n-bit vectors. And they're just, we make the first row out of these things, and then the second row is just the same as the first row, except shifted to the right by n places, okay, where n is the size of these vectors. Okay, so an example here, again, same code. So we have our little G0 vector would be 2 1s. Our G1 vector would be a 0 and a 1. And our G2 vector would be 2 1s. And the generator matrix then would look like this. Okay, and for this input sequence, we would simply add rows 1, 3, 4, and 5 of the generator matrix to get the corresponding code word. So we'd get 1, 1, 0, 1, and then here we got to add row 3. We're going to get 0, 0. We don't have anything else left here, but we're adding 3 and 4. We're going to get 1, 0. And then here we're adding 3, 4, and 5. We're going to get 0, 1. And then here we're going to get 1, 0 again. Here we're going to get 1, 1. And then there's nothing, there's no ones after this, so that's, the rest would be all zeros. So this should be, if we look back in the notes, the same V that we wrote before, because we were taking the same input sequence. So again, you can think of doing this, and there's another way we're going to see in a minute. You can think of doing this by generating the code sequences out of a convolutional encoder. I mean, you can look at it a number of ways. You can just look at the encoder diagram and do the math right from the encoder diagram. You can do the discrete convolution. You can use the generator matrix, and then we're going to see shortly there's something, a way to do it with generator polynomials. And that's next. So the polynomial representation, an output sequence, the ith output sequence can be written as the input sequence u expressed in polynomial form with an indeterminate d as a delay element, times the generator, the ith generator sequence, again written with in polynomial form. This is like a d transform type of thing, or I guess it's, in linear system theory, it would be essentially a z transform type of operation, except it would be, here we're using d because it represents a one-time unit delay. So for example, the G1 of sequence 101 can be written in the transform domain as 1 plus d squared. Okay, and 111 can be written as 1 plus d squared. And the u of d can be written just as a polynomial like this, where we get 1 plus d squared plus d cubed plus d to the 4th. And the discrete convolution, just like any linear system, you can replace convolution in the time domain with multiplication in the transform domain. So in the transform domain, we just have to multiply the input polynomial by the generator polynomial to get the corresponding output polynomial. And in this case, if we do this, we can see when we multiply 1 plus d squared by u of d, multiplying u of d by 1 gives us 1 plus d squared plus d cubed plus d to the fourth. Multiplying it by d squared just gives us four additional terms, d squared plus d to the fourth plus d to the fifth plus d to the sixth. And there was a d squared in both of those, so they cancel out. And there was a, let's see, we had 1 plus d squared d cubed d to the fourth, and then we got d squared d to the fourth. There's also a d to the fourth in both, so that cancels out. And we're left with 1 plus d cubed plus d to the fifth plus d to the sixth. So this is usually easier. I mean, if you're just playing with this kind of thing by hand, it's usually easier to just use the transform domain. And if you multiply u of d by 1 plus d squared, you get this polynomial. And again, you're going to get, you have 3 terms here and 4 terms here. So when you multiply it out, you're going to get 12 terms. But there's going to be 4 pairs of cancellations where the d would have the same power. So you're adding the coefficients. 1 plus 1 is 0, so those terms drop out, and you're left with these 4. So if the input sequence, and then you really have then a block code. If you look at the big generator matrix associated with that input sequences of that length, you can also view it as a block code. So this is called, in convolutional term code language, termination. You terminate a convolutional encoder, and when you terminate a convolutional encoder, you generate a block code. So actually, in some sense, convolutional encoders, especially simple convolutional encoders, like with just memory 2 like this, they can be used to generate large block codes just by using them, putting long information sequences into convolutional codes, simple convolutional encoders. You can generate big block codes that way. Now, as a long block code, they're not particularly powerful in terms of their distance properties and things like this, but their complexity would be much less of encoding and decoding than a normal block code of that size. Okay, so you can look at these things this way. Now, I wanted to just pause here and just, I don't think, was there another question, or? I don't think we need to raise the screen, but I just want to make the point, because I didn't see it in the notes, that we can, in the transform domain, we can also consider a transform generator matrix, which in this case would look like this. Otherwise, the 2 generator polynomials can be considered as part of a 1 by 2 generator matrix. And then we can write the code word v of d. Now, again, because I've kind of used v of d here in a little different way, actually I didn't mention that, I'm going to put an underbar here. Again, there's different ways of writing these things, and it doesn't matter so much which way you do it. As long as you don't get confused between the different ways. But in this case, I mean v of d to be this v1 of d, v2 of d, the 2 output sequences separately. And that's simply given then by u of d times g of d. Okay, so you multiply the information polynomial u of d by g of d. You're multiplying u of d by g1, which is what we're doing right here to get v1. Okay, and you're multiplying u of d by g2 to get v2. So you have not only the generator matrix, the binary generator matrix that we showed, but you have a polynomial generator matrix also. It's k by n, 1 by 2 in this case. And in general, you'd fill out this k by n polynomial generator matrix with n, k times n generator polynomials. In this case, there's 2. Oh, I was going to mention this. This is just another way of writing. You again, if you want to write, so here we have the n different output sequences. If you want to write them in polynomial form, all as one sequence, the same way we did with the time domain vector when we interleave these two things together, you can do it this way. I mean, you can just, you take the v1 sequence this and replace d by d squared, take the v2 sequence, replace d by d squared, and delay the v2 sequence by 1, and then you get these two sequences interleaved together as one sequence. You can check, I mean, it's not important. You can check, just write one out if you want and see that that's a way you can represent it. So all we're saying here is we can get this form from the polynomials, we can do that this way. We get v1 of d and v2 of d this way, and then do this, and we wind up with v of d, which would just be this sequence written in terms of the delay elements. In this case, it'd be 1 plus d cubed plus d to the 6th plus d to the 9th, etc. So this is yet another way of writing these things. You can write a kind of a composite generator polynomial where you kind of do the same thing. You take each of the generator polynomials, replace d by d to the n, and then delay each one by 1 time unit compared to the one in front of it. So you get what we call a composite generator polynomial, and then you can multiply that by the input sequence with d replaced by d to the n. So that's the kind of interleaving of these sequences built into the notation here. And you can get v of d then, which is this thing written as a polynomial, or what we have here, the same thing we have written here, you can get it in one equation, if you like, rather than doing it separately n times. So again, these things are not such a big deal. It's just notation and indication that we can write these sequences in different ways. So in the time domain, here was our sequence. In the transform domain, if we want to do it this way, we could get that directly by, we take u of d squared, which u of d was 1 plus d cubed, or plus, no, what was u of d? 1 plus d squared plus d cubed plus d to the 4th in this example. So u of d squared would be 1 plus d to the 4th plus d to the 6th plus d to the 8th, just replacing d by d squared, so the powers are all doubled. And we multiply that by this g of d polynomial, which is, in our case, it would be g1 of d squared. g1 of d was 1 plus d squared. So g1 of d squared would be 1 plus d to the 4th. And g2 of d was 1 plus d squared. So that would be 1 plus d squared plus d to the 4th. Delayed would be d plus d cubed plus d to the 5th. So I think we've got all that in here. D plus d cubed plus d to the 5th. That's the three terms from this. And 1 plus d squared, these two terms come from here. So this polynomial corresponds to these two terms from this composite generator polynomial. And this polynomial corresponds to the input sequence u, again spread out, so each input is delayed by 2 time units. And if you multiply these two together, you get this, which should correspond to this. 1 plus d cubed plus d to the 6th I think this is what I read off earlier, plus d to the ninth, etc. Okay, it's probably seems more complicated than it is now. I think if you keep the little example in mind, you're fine, okay? There's just several different ways of looking at this and writing the equations depending on what you're more comfortable with. Okay, I think most people like the polynomial representation. It's just easier. It's like it's multiplication instead of convolution, etc. There's various ways of representing these different generator sequences and code sequences in a convolutional encoder, but the basic concepts are pretty straightforward.
Why do books still have, because the polynomial representation is much compact and easier, why don't books just start directly from that? Convolutional code with convolution and then want to relate that in block codes also we have this matrix form, so they want to show, because it's...
I don't know what other people do, but the reason I did it is because I like to, I mean, they're convolutional codes. So they are, so these are linear systems. These are linear time invariant systems. And so you want to get the idea, the whole linear systems analogy, I think, between convolutional encoders and using both the time domain and the transform domain. Yeah, I think, but you know, quickly the time domain is kind of done away with and you use the transform domain for most of your work. But I think it's worthwhile to start out with the time domain just so people see that it is convolution and it's a discrete convolution, and that's actually what's happening. I don't know if the other books still do that or not.
Because it's much easier to do things in the transform.
It is, yeah, and that's. But I think if you just do that, you tend to forget about the fact that it is a linear time invariant system, and we didn't spend a lot of time in this class talking about that, but that's certainly the case. Okay, now there's something called, it's a sequential circuit, so it can be represented by a state diagram, just like any sequential circuit. So that turns out to be useful in terms of visualizing the properties of a convolutional encoder. So we start out by defining what we refer to as the state, and it's just the contents of the shift register. And for an N1M code at time instant L, the state's defined by this M tuple. Okay, because the current input bit is well, actually, okay, it looks like we've switched. Okay, we're using X here to represent the state. You're going to tell me why.
Because of feedback,
oh yeah, okay, okay.
Feed
Yeah,
forward, you can
right.
put
U,
minus,
right,
but
right.
So to take care of feedback, I just changed it.
Was that in my book?
No, it wasn't. I
Okay.
just changed it to X because
Okay.
that was creating a problem
Yeah.
with feedback at modem.
Yeah, that's a good point, because when you have a feed-forward encoder, and we'll get to this, the input bits are just, the stored bits are just past input bits. But when you have feedback, you have output bits fed back, so those are also stored. So rather than just use U as the contents of the shift register, we'll use X. Now, if it's a feed-forward encoder, those are the only kind we've looked at so far. The X's will just be the U's. Okay. And so there's 2 to the m possible states, because the state vector is of length m. Everything is binary. Okay. And this is important because the complexity of decoding is dependent on the number of states. There's a maximum likelihood decoding method and a map decoding method. Those will be both discussed tomorrow morning for convolutional codes. And their complexity depends on the number of states. So that's, that also relates to some of the stuff we'll do later this afternoon. Because of that, we would like to keep the number of states small if possible. Okay, although if you want a powerful code, you've got to make the number of states large. So there's always that trade-off. So the output of a convolutional code at any time is it depends on the input and the current state. And if you think back to the encoder diagram, it's clear. You've got, at a particular time, you've got certain bits stored in the register, and you've got that's the state. Those bits correspond to the state. And then you have an input bit, okay, and the output is a function of the input bit plus the state. Okay, that's just a general way of looking at the encoding equations here. Yet another way of looking at the encoding equations. And not so much in terms of generator sequences or generator polynomials, but in terms of the state, in terms of what's stored in the shift register. So each time a new information bit enters the encoder, it goes through a state transition, otherwise the state changes. So at time unit L, you have a message bit U sub L, and say this is your state, okay? Then at time unit L plus 1, you get a new message bit in, and the contents of the first M minus 1 stages of the register, they shift, and they're now the last M minus 1 states of the register, and then a new bit comes in and occupies the first state of the register. So the fact that the first M minus 1 bits here shift down, and a new bit shifts in the beginning, okay, gives you a new state. Now even that can be, the state change like this doesn't always have to be this way, because there are ways of realizing the encoder where you can have the diagrams we've showed show there's no there's no possibility of adding anything into the intermediate stages of the shift register. But actually there are encoder realizations where you could do that. And that would mean when you go to a next state, you may not, these M minus 1 bits may not exactly reproduce these M minus 1. Okay. But in any case, when a new bit comes in and the register shifts, we're in a new state. We'll see if I remember when we get to some of these other encoder diagrams, if I remember to point that out. A state transition is represented by a directed edge connecting two states. I'll go through this quickly because it'll be easier when we look at the example. And the transitions are labeled with the information bit that caused the transmission, this message bit, and the coded bits that come out of the encoder as a result of that transmission. So here's our same little example. And here's the state diagram. And we get this, we can look at this and derive this. So here what we're saying, this represents the 0 state, where there's nothing stored in the register. And in fact, with the memory 2 here, with the 2-state shift register, there's clearly 4 states. So we need a state diagram with 4 states. And they're going to be 0, 0, 1, 0, 0, 1, or 1, 1. Those are going to be the 4 possible states. If we're in state 0, 0, so we have 0, 0, and we put in a 0, we're going to get zeros out, clearly. And our next state is still going to be 0, 0. So that's represented here. We have an input 0. We have 2 output zeros, and we stay in the state 0, 0. There is a line dividing the first bit in each of these labels is the input bit, and then there's a line, and then the next 2 bits are the corresponding output bits. But when we put in a 1 here, we're going to get a 1 out here and a 1 out here. And then our next state is going to be the 0 here shifts down and the 1 shifts here, so our next state is going to be 1, 0. So that's represented here. When we put in a 1, we go to state 1, 0, and we get 2 output 1s. Okay, it's a little small on the diagram here, but you should be able to see it in your notes. And so we can fill out the entire state diagram that way. If we're in state 1, 0 now, and so we have a 1 here and a 0 here, and we put in a 0, we're going to get a 0 out up here, but we're going to get a 1 out down here because of this 1. So our outputs are going to be 0, 1, and the next state will be the 0 will shift here and the 1 will shift down there. So the next state's going to be 0, 1 also. So if we're here and we put in a 0, we go to state 0, 1, and the outputs are 0, 1. If we put in a 1, we're going to get a 1 out up here and a 0 out down here. And we're going to go to state 1, 1. Because we had a 1 here, it'll shift down, we get a new 1 coming in here. So we have a 1 and a 0 output and going to state 1, 1. So again, state 1, 0, we put in a 1, we have a 1, 0 output, and we go to state 1, 1. So it's easy to fill the state diagram out directly from the encoder diagram like this. Now, what I was saying earlier is, just so we don't lose the thought, when we have, this is called a feed-forward encoder. When we have a feed-forward encoder like this, the state is always the past, the M past input bits. But as Adrich was saying, we can also have feedback encoders, so the output can be fed back, and there can be an adder here, okay? And then what comes in here is not just this input bit, but this input bit plus whatever was fed back, okay? You can also have realizations of encoders where you'll have inputs into the middle, maybe an adder here where an input is put in there. And then this simply shifting down of input bits would not be the correspond to the state transition necessarily. But in any case, you look at the encoder diagram, you can always figure out what the sequence of states is going to be. Is there any question on where this state diagram comes from? So this is fairly, I mean, if you're familiar at all with, you've done sequential logic and stuff like that, this is pretty easy to follow. Now a Trellis diagram is basically an expanded state diagram. Notice the state diagram, it doesn't, there's no sense of time in the state diagram. Oh, I should point something out here though. You can always, if you have the state diagram, you can figure out any code word corresponding to any input sequence. We always assume we start in the all zero state. And if you put an input sequence, say 1, 0, 1, 0, 1, you just follow along here. Here's a 1, and you get the 2 output 1s. You get to here. Then you put in a 0. You get a 0, 1 out. Then what did I say? You put in a 1. That takes you back along this path, because this corresponds to an input of 1. Gives you 2 0 outputs. And then you put in another 0, I think I said. That takes you back along here, which gives you a 0, 1. And then I believe I said you put in another 1, would take you back here, again with 2 0 outputs. And maybe you do another 1 then, and another 0, and another 0. In any case, whatever input sequence you put in, if you have the state diagram, you know everything too. Okay, you can figure out everything. Whatever input sequence you put in, you can just follow it around and read the encoded bits off the labels of the paths, and that's the corresponding code sequence. You can do the same thing with a Trellis diagram. The only difference is the Trellis diagram is kind of a state diagram expanded in time. So it's a separate state diagram shown at each time unit. And it's repetitive, because if it weren't repetitive, you couldn't draw a state diagram which would represent all time units. We'll see that in a second. So again, the wording here is, we'll see in the example, I think, easier than trying to follow the exact wording. But in each Trellis section, the states are represented twice. We have a set of states at one time unit and then a set of states at the next time unit, say L and L plus 1. And there's a branch connecting a state at time L to a state at time L plus 1. If there's an input at time L that takes the encoder to state L plus 1. So for example, if we were in state 1, 0, there's going to be a branch connecting state 1, 0 at time L to states 0, 1, and 1, 1 at time L plus 1, because you can get here and you can get here from this state. You can't get back here from this state. So there'll be no branch connecting 1, 0 back to 0, 0. We'll see that in a second. And so you have these, you kind of have two state diagrams with the connections between them, and then you just replicate that, each one representing a different time unit. Now you may think, why bother doing this? You'll see, I think it'll be easier to see, because you've got the state diagram, why do you need this thing? We'll see tomorrow when we discuss the decoding algorithms that this gives the visualization that you need to really understand the decoding algorithms. Much easier than you could just by looking at the state diagram. So the code word is made up of the labels on the trellis transitions that correspond to a specific path through the trellis, just like a code word corresponded to the labels on the state diagram transitions that corresponded to a specific path through the state diagram. Now here we've got a different, example here. Here's one of the feedback, okay? So the output is fed back here. So this is a rate 1/2 encoder. It's what we're going to call systematic. We'll talk about this more next time, which means that one of the output sequences is the input sequence itself, just like with block codes, where the message block is itself part of the code word. And then in this case, the second output sequence is obtained by the generator polynomial. So the generator polynomial that generates V1 is just 1. It's U of D times 1 is equal to V1 of D. But the generator polynomial that generates V2 is actually given by 1 plus D squared. So we have the input bit here to the register plus the delayed by 2 time units bit added together. But this bit has actually been divided by, this would be 1 plus D squared. Otherwise what goes in here is the input bit, and also the contents of both of these registers fed back. So this input represents 1, this input represents D, and this input represents D squared. So actually the generator matrix for this code, for this encoder, okay, again, it's rate 1/2, so the first one is 1, and the second one is 1 plus D squared over 1 plus D squared. So it's a feedback encoder. Now, we'll say more about this next time, but here I just want to look at the state diagram and the trellis diagram. But that is the, and if you've done this type of thing with linear systems, you kind of know how this works. So here's the state diagram. Let's see if we can figure it out. We won't do the whole thing, but it's going to be a little different and a little trickier than the other one. So say we'll start with the easiest case, 0, 0. We put a 0 in. Of course, we're always going to get the self loop around the 0 state, 0 in with 2 0 outs, and we stay in the 0 state. Now what if we put a 1 in? Okay, well we're going to get a 1 out up here, but that's it, because, oh no, excuse me, that's not it. We have the 1 coming in here, 0's fed back, so we get a 1 coming out here. So we're going to get 1, 1. With the 1 input, we're going to get a 1, 1, and we have to see what the state is. So that 1 that gets fed up here, then the next time unit will move over here. And the 0 that was here will move down here. So the next state is going to be 1, 0.
This thing is, I think I wrote it differently. Since I think I wrote it as
It should be 1, 0, right?
right, but
Yeah.
I wrote it as this. This is the last one, d square, as the most significant. So I wrote it with the 1, 0 that moved in. I wrote it as 0, 1.
Okay, so
In the notation that I have, the
so
one
you're saying that this is the first bit and this is
yeah,
the second
that's what
bit.
I wrote in there.
So if we could just turn that around and say that that's 1, 0. Let's see if that works. So let's just think of this as 1, 0. And then we've got a 1 input from the 1, 0. Okay, or let's start with the 0 input from the 1, 0. So we have 1 here and a 0 here, and we have a 0 input. Okay. The 1 here gets fed back, so we have 0 plus 1 is 1. By the way, the 0 input is going to give a 0 out here. The 1 gets fed back, so we're going to have a 1 here. 1 plus 0 is 1. So we're going to have 0, 1 coming out. And the 1 that was here is going to shift down here. And the 1 that gets fed back is going to shift over here. So we should get 0, 1, and the next state should be 1, 1. And that's what we do have. We get a 0 input, we have 0, 1 out, and the next state is 1, 1. And again, I'm thinking of this as 1, 0. Okay. And then if we put a 1 in here, we would, so we have a 1 out up here, because it's systematic. We have a 1 here. Our state was 1, 0, so we feed back a 1, we get a 0 here. So we have a 1, 0 out, we have a 0 here. It shifts down here, and the 1 shifts down here, so we'd go to 0, 1, which will show up as 1, 0 on the thing. So yeah, we have a 1 input, we get a 1, 0 out, we go to, which doing it the other way would be state 0, 1. So again, you can fill out this state diagram. This is just a second example of doing a state diagram. I think the point here is when you have encoders with feedback, it's a little more complicated, not as straightforward as it is with feed-forward encoders. But there's good reason to have encoders with feedback in some cases. Okay, so it's not a case which can be ignored. What does the Trellis diagram look like then? And it's for this state diagram, not for the one in our previous example. Well, at each time unit, and this kind of extends back in the past and forward in the future. This is just a little section of the middle, if you want. There's one section of this Trellis diagram for each input bit. So depending on how long the input sequence is, would depend on how long the Trellis diagram is. So this is time running this way. And we have our 4 states at each time unit. And again, from the state 0, 0, we either stayed there or we went to the 0, 1 state, or the 1, 0 if we switch them, with 1, 1 outputs. And the other case we looked is when we left here, we went either to this state or to this state with these outputs. And again, the branch labels here are just like we label them with the state diagram. The first bit is the input bit, then after the slash is the 2 output bits. And then we can follow any input sequence, we can follow it through the Trellis diagram, similar to what we described for the state diagram, and we can find out the corresponding code sequence. So if our input sequence was 1, 1, 1, we would have an output sequence 1, 1, 1, 0, 1, 1. And that would take us back to the all 0 state. which again is a feature of feedback encoders that is different from feed-forward. If you have a feed-forward encoder with memory M, you always need M zeros at the end to get the encoder back to the 0 state, because the encoder state is just filled up with inputs. So to get back to 0, you need M zeros. But with feedback, that's not true. So actually, we start in the 0 state, we put in 3 ones, and we get back to the 0 state in this example. So the feedback encoders are not quite as intuitive as the feed-forward encoders, but they're basically in 2 very practical applications of convolutional codes. One is in modem applications, high-speed modems, where you use high-rate convolutional codes, and it's common to express these, to use feedback encoders for these codes. And in other cases, in turbo codes, the encoders that you use for turbo codes really need to be feedback encoders. In the case of high-speed modems, it's convenient to use the feedback form of encoder, but it's not necessary. It makes things easier, some of the analysis. But in the case of turbo codes, it's essential that you use feedback encoders, systematic feedback encoders. Any questions on this?
No,
You don't have to. I mean, it depends on how you want to think of this. As if you want to think of the first bit here in the state as being associated with here or here. The way I was thinking of it, the first bit here would be associated with this register stage. So then if you want to think of it that way, you would turn these 2 labels around. Everything else stays the same. But if you're okay with thinking of, it's kind of arbitrary how you define the state, which order you take the bits in. So, yeah.
This feedback convolution encoder resembles an IIR filter structure. So I was thinking
Yeah.
there are any stability issues, but since the arithmetic is modular, there might not be any.
There's no stability issues in the encoding, but it is an IIR, encoder. And there are some consequences to that, which the very next class we'll discuss that a little bit. Any other question on this?
Two states have to be flushed down to 0, all zeros. So how does that monitor the impact? Conventional hardware. Does it monitor?
Well, I mean, you say they have to be. I mean, normally when you encode, it depends how you're decoding. If you're decoding using the Viterbi algorithm, which is optimum, you need to return the encoder to the all 0 state, okay? And you do that by putting, if it's feed forward, by putting zeros in at the end. If it's feedback, you have to compute the bits that need to be put in to get you back to the 0 state. But you don't necessarily, I mean, there are things called tail-biting codes which operate a little bit differently, in which you don't force the encoder back to the all 0 state. But there you have to also do a computation, because you do have to start and end in the same state. So you have to do a computation as to what state you should start in for your particular input sequence in order to wind up in that same state. And why would you bother with all that complication? Well, when you do terminate these things by forcing them back to the 0 state, there's a little bit of rate loss involved. Otherwise, we're talking about a rate 1/2 encoder here. But the last 2 input bits, if you want to force back the all 0 state, have to be zeros. So they're not, or the last M input bits in general. So they're not information bits. So the rate is then, when you talk about a terminated encoder, it's slightly less than 1/2, depending on how long the sequence is. I mean, if you're sending 1 million bits, and then you just add 2 termination bits, you lose almost nothing. But if the sequences are shorter or if the memory's larger, there's a rate loss involved. And if that's a problem, you can use this tail biting encoding, in which you don't go back to the all 0 state, but you start and stop in a state depending on what your input sequence is, but you have to calculate that. But there's no rate loss. So there's some issues like this, yes.